Welcome back to week 7, and in video 3 we're going to talk about some of the effects of earthquake activity and how earthquakes are related to the interior of the earth. So I want to show you some of the things that can happen. So basically, when you have an earthquake, buildings are destroyed. It's kind of an obvious one. You can get tsunamis produced and flooding, liquefaction of the ground and causing buildings to collapse, and then slope failure. This is an image here showing you one of these slope failures. This is a railroad line in up in Olympia, Washington, and you can see the land just slid out right underneath it because the ground was shaking, became unstable, and just gave way. We also can have liquefaction that can produce things called sand boils. So basically the ground shakes so much that any water that's down in the ground gets jiggled around. You can get these basically like little eruptions, mini volcanic eruptions of sand and water to the surface. Pretty amazing. So this is a fracture in the ground underneath the railroad that produced these sand boils. So the question is, well, what the heck is liquefaction? Well, I've got a great image here of this little movie. Shaking, and then the house sinks in it. Pretty interesting. Watch that again. You can see a person's leg here. If you were standing and you had the ground shaking, we have the grains in the ground all shaking together, compacting more, and acting like quicksand, and the whole house or structure can sink into it. And so some of the features that we produce and hazards that end up happening is here. You can see this is June 16th, 1964, earthquake in Japan, where the ground liquefied and these buildings just toppled over completely over to the sides. Just absolutely unreal. And this liquefaction tends to happen in unconsolidated sediments, so things like sand, gravel, silt, mud, artificial fill. Those are all very dangerous substrates to build on. When you think about Portland, well, Portland is in a river valley, and it is built on mostly loose sediment. Now, if the buildings are, if the foundations reach down to the bedrock, then buildings are in a much safer situation. So they're tied to the much more stable structures, so the shaking won't be amplified by the loose sediments that are around. And here you can see a bridge that was taken out by liquefaction, and also a tsunami was produced here as well. 1906 San Francisco earthquake, same thing. Magnitude 8.3, huge earthquake that to occur in the US in the 20th century, and you can see liquefaction again causing this house to sink into the ground and tilt over, buildings collapse due to not being prepared or earthquake prone or earthquake ready structure. So hopefully now in a lot of these cities, you'll notice, especially in Portland, a lot of retrofitting happening, and that's a way of taking an old building and trying to make it more stable, so if the big earthquake hits in the Pacific Northwest, that the buildings won't necessarily collapse, or it won't be a detrimental event. But things aren't quite ready for the big one. In 1989, the Loma Prieta earthquake in California. You can see this one. This was a big earthquake, also a tsunami produced. And in this case here, incredibly deadly. This overpass here, it was 2 layers, as you can see here. It was an underneath and a top, and the whole thing just pancaked, completely flattened. And there were 41 people that were killed by the collapse of this double-decker highway structure, because it just was not ready for the massive shaking that occurred. You see this happening in a lot of places. The buildings aren't ready, structures aren't built to withstand that amount of shaking, so things unfortunately end up collapsing. Now, we've learned from these earthquakes, so we can build structures that may be able to withstand that shaking a little bit better. We know what liquefaction is, we can determine what the substrate is, and hopefully build in a little bit safer areas. We also can see landslides. Here you can see one covering this whole road, surface fractures opening up, buildings toppling and collapsing. This is the 1994 Northridge, California earthquake. You can see one of those pillars just totally demolished here. This parking structure in California just totally collapsed over, not quite sturdy enough. In 2010, Chile earthquake produced a lot of damage. You can see some structure here totally devastated, and then the tsunami that was also created by this shaking brought huge ships up onto the land. Same thing in the 2004 Sumatra, Indonesia earthquake. The tsunami produced, you can see this tree totally submerged, the murky water just inundating this hotel, and then the damage by the earthquake and tsunami down here. Now there's a great video here, NOAA tsunami websites. If you visit this website, you can see lots of great information about all this stuff. And then there's also this great video that I've posted. It's video 6. Watch it, especially if you're going to the coast anytime soon. It's gives you some very interesting and useful information, especially if you have a house out at the coast, visit the coast very often. Definitely watch that video, because tsunami information that might be on your quiz will be covered in that video. So how do earthquakes relate and tell us information about the interior of the earth? Well, based on these earthquakes that happen, we've got an epicenter located on one side of the planet, and then seismic stations set up all around the world. We can actually trace that earthquake and see where it is picked up around the world. And basically what we noticed is we see that there is this P-wave shadow zone that occurs, and also an S-wave shadow zone. So basically what happens, the P-waves, as the P-wave travel through the liquid or partially liquid core layer, they start to slow down. And then once they reach that more dense rock layer in the earth, they speed up again. So that tells us there's some change happening inside the earth. We also see an S-wave shadow zone as well. It's much larger. It's the whole entire other side of the earth, because S-waves cannot travel through liquids at all. And your textbook has some great diagrams and images showing you exactly this, the same idea. So definitely check those out. It's all because of S-waves not being able to travel through liquids, so we know there's a liquid area inside the earth, and that when we have cooler rocks, they're more dense. P-waves travel much faster through them. When they're warm or liquid, they're going to travel slower, get slowed down, and we result in this shadow zone. So with higher tech equipment that we have now, it's more sensitive. We can actually determine where we have plates that are colliding, where we have plates that are starting to melt, where we have big magma plutons below the earth. We can actually start seeing that kind of data coming out of this earthquake simulations, which is pretty neat stuff. And if you have questions about how we use those, and if you want to see some neat figures, just let me know in lab. So that kind of wraps up earthquakes. We'll come back and talk about plate tectonics.